Welcome back. Today we're going to talk about antiderivative. This is the last section from chapter 3, and it's an introduction to the next chapter. What is antiderivative? So far we know if you're given a function, you can take the derivative from that function. If the function is differentiable at specific points, you can calculate the derivative at that point. So now in this section, what we're going to discuss is, what if you're given the derivative, can you go backward and find the original function? And is it possible to do such thing? And do you get a unique function by taking an antiderivative? So here, let's start with the definition. Function capital F is called the antiderivative for the function f if you take the derivative of the capital function and you get the small f function. So what does it mean? That means if you're given the capital F function, by taking the derivative from that, you get f, the small f. Therefore, by going backward from small f, you should get the capital F function. It's not exactly by going backward because there is a small change. Let's say if I tell you the derivative for a function is 0, what you can tell me is that original function should have been a constant, something like 3, 4, 5. But it could be any of those numbers. It could be pi, it could be 7, 11, doesn't really matter. So what we can say is this theorem should make sense that if f is the antiderivative for a function f, small f, then any constant added to the capital F function is still an antiderivative. Because by taking the derivative of this capital F function plus any constant, the derivative of the constant will disappear. So therefore, there is a general, this capital F plus C is called the general antiderivative. The capital F is specific, it's a particular antiderivative. By adding all the constant possibilities, then we make it a general solution. So here are a bunch of examples. They say find the most general antiderivative. That means consider this constant C involved. So here, let's think about this. Given a function f as sine x, if I ask you to find the derivative of f, if I tell you find out what is f prime x, you should say the derivative of sine is simply cosine x, and that's it. But that's not the question at this moment. The question is, what if I tell you the derivative of the capital F function is given and it is sine x? Can you guess what the original function was? We know the original function should be something like cosine. But what is the derivative of cosine? The derivative of cosine is negative sine. So if I put a negative here, then the derivative of negative cosine x is simply sine x. This would be correct. But is that the only solution? Not really. If I added 2, this is still correct. The derivative of f of x derivative would be f prime, which is sine x. If I add 20, still the derivative is sine x. So any constant added to this function, positive or negative, still has that derivative of sine x. So capital F function is simply negative cosine x plus some constant. How about the next example? What if you're given 3x squared as a derivative, and they say find out what is the capital F function? Capital F function should be derivative of what polynomial, in this case x to the power 3. Derivative of x to the power 3 is simply 3x squared. So what we're checking is to see if these two match. If this is true or not. Derivative of x cubed, simply 3x squared. So this is a true statement. But any combination of constants added to this function still satisfies this property that the derivative is equal to f of x. And this is not guessing. When you take the derivative of the x to the power 3, what you do is you drag down the exponent, subtract 1 from the exponent. What we're going to do is try to find a method to go backward in taking the derivative. So here, what if it was x squared, not 3x squared? What would be the derivative? The antiderivative. So if we picked only x cubed, the derivative should have been 3x squared. Remember, there should be a 3 here. But in this case, there is no 3 there. So it means I need to multiply a 1/3. This way, if I take the derivative of 1/3 x cubed, what do I get is 1/3 times 3x squared. The 1/3 and 3 will cancel out. So the derivative here would be 1/3 times 3x squared. So therefore, these two will cancel out and I simply get the x squared that I needed. So this 1/3 is just to get rid of that exponent 3 when you drag down the exponent. Okay, so we can regenerate this idea for any other case, something like x to the power -5. What would be the antiderivative? Normally, you subtract 1 from the exponent, but now here you see that from x squared, we added 1 to go backward. So what we do is we add 1 to the exponent, x to the -4. And you should have a 1 over -4 since when you take the derivative, if you calculate the derivative, it would be 1 over -4 multiplied by the derivative of the exponent, -4 times x to the power -4 minus 1, -5. These two will cancel out and you get exactly x to the -5. And any combination of c, any constant added, still this is the true antiderivative. So we can build the general formula, which is basically for all these trigonometric function and exponential function, not exponential, sorry, polynomial cases, we can build such an antiderivative instruction. Remember, if you're given a constant multiplied by a function when you take the derivative, you keep the constant and multiply the derivative later. So we have a similar idea that if you want to find the antiderivative, so if you're given the f prime, and they say find out what is the original f, yeah, I'm going to find out this as a particular f. If you're given the derivative and they ask you to find the antiderivative, so if they want to find the antiderivative, still the same properties holds. Constant multiplied by a function, you can keep the constant multiplied by the antiderivative later. If you have two functions added to each other and you want to find the antiderivative, you can find the antiderivative of each one separately and then add them together. The same with the subtraction is true. It was subtraction. If it was x to some power, we would drag down the exponent, subtract 1 from the exponent. But here now, we add 1 to the exponent. We're going backward. And to get rid of the coefficient created by that, we divide by the same exponent. So you can write this 1 over n plus 1, or this is the same as, or x to the n plus 1 divided by n plus 1. That's the same thing. So you add 1 to the exponent, divide by the same exponent. That's how you take the antiderivative. For trigonometric functions, if you're given cosine as the derivative, we know the original function should be sine x, because the derivative of sine is simply cosine. What if you're given sine? We already discussed this. The derivative of cosine would have been negative sine, so to get rid of that negative, we multiply a negative here. What is the derivative of what function is secant squared? We should know that tangent has derivative as secant squared. Derivative of what function is secant tangent? That should be secant x. And cosecant squared was derivative of cotangent. Derivative of cotangent would have been negative cosecant squared. But since we don't have that negative, we will add the negative here. Because then now the derivative of negative cotangent x would be negative times negative cosecant squared, which is simply cosecant squared. And similarly, you will have negative cosecant x here. All these are the particular case. The general you should have a plus constant c everywhere. If it was the case of we're looking for the general case. So let's use this idea. Again, we did these examples. These are the basic ones. We will build later as we talk about the integrals. We will discuss these more often, but now these are the particular cases. So here, let's see. Given a function f, and the given information is the derivative of f is given 4 square root of x plus 1. Then we want to find out what is the original function f. So you see that there is no capital function used here. We already have given the derivative as f prime. In the last examples here, up here, what you're given is the capital F, the small f, as you look at this as the same as f prime. And we're asking what is the original function f. That's what in this sense here the small f means. But now in these examples, what you notice is you're asking to find f if the derivative is given in this form. So how do we find the antiderivative function f? If you wanted to take the derivative of the function 4 square root of x plus 1, what we do is you write it in terms of x to the power 1/2. So what I'm going to do is I'm going to think about f prime x as 4 times x to the power 1/2 plus 1, and say, now if I want to go backward and say what is, so the question becomes, what is the antiderivative of f prime of, let me say, 4 x to the power 1/2 then plus 1. Okay, you can calculate each one separately, which means you can calculate derivative of x to the power, antiderivative of x to the power 1/2, antiderivative of 1, antiderivative of 4x to the power 1/2, antiderivative of 1, and find out what is their summation later. So if I say the derivative, let me stick with this notations. I don't want to introduce new notations so you get confused. So here, let's say, what is the antiderivative of 4x to the power 1/2? Ignore the 4. What would be the antiderivative of x to the power 1/2? As I mentioned above, you add 1 to the exponent, so 1/2 plus 1, divide by the same exponent, 3/2. 1/2 plus 1 is simply 3/2. I should have added here as well. So 3/2. We added 1 to the exponent. What is the antiderivative of 1? Derivative of something is 1. What is that? That's simply x. Derivative of x must be 1, so the antiderivative of 1 is simply x. And so this gives you the function f, the original function. But this may not be the exact function because you can add any constant to it and still has the derivative of 4x to the power 1/2 plus 1. So we know the f of x has this format, but we don't know what is that constant c. This constant c, we don't know what it is. So here is the extra information given. Given at 1 for x, we know the function must be 2. So we have to figure out what that constant c is by using this extra information that given f of 1 equals to 2. So first, let me simplify this function. You can multiply 3/2 to both numerator and denominator. Sorry, 2/3 both numerator and denominator, and simplify this as 8/3. X to the power 3/2 is square root of x cubed, and plus x plus c. This is the simplified version of f. So since we know f of 1 is given 2, that means if you replace 1 into the function, you expect to get 2. That means if I replace 1, I should have 8/3, 1 cubed plus 1 plus c. This summation must end up to be 2. Because replacing 1 for the x should give you y value of 2. So now it's just a simple calculation. Square root of 1 cubed is still 1 times 8/3 plus 1. So this adds up to be 11/3 plus some constant c equals 2. We can figure out what that constant c is by subtracting 11/3. So this is minus 6/3, so negative 5/3. Okay, so now I can answer the question. What is the function f? F of x is exactly 8/3 square root of x cubed plus x plus, we figured out what is that constant. That constant is negative 5/3, so I'm going to replace it with negative 5/3. So this is a particular function f that satisfies both of these two equations. It has this derivative as well as the evaluated at 0.1, it should give you y value of 2. Okay, so this is one example. A similar example could be done for higher derivatives. So here's an example that if you're given this 2 derivatives, they ask you find out what is the antiderivative, find original function. So what's given is the second derivative as 12x squared plus 6x with 2 extra information. These are for those constants that will show up. And you want to find out what is the original function f. So first, as if you wanted to take the second derivative, first you need to take the first derivative, then the second derivative. So first we need to figure out what is the first derivative. So it means find the antiderivative of 12x squared plus 6x. Keep the 12. What is the antiderivative of x squared? It should be x cubed divided by 3. Why am I writing the antiderivative? Because I'm already assuming that I'm finding f prime. You cannot write f double prime and write this. This means I'm looking for the first derivative, which means go backward in the derivative one time. So we added 1 to the exponent, divide by the same exponent, plus 6 is still there, constant, and add 1 to the exponent of x. If you add 1, what you get is x to the power 2 divided by 2, plus some constant c. So now, how do we figure out what is this c? Look at what the function is. The function to be found is f prime. And the information given for f prime here is f prime at 0 equals to -1. You cannot use the information for f of 1 because that's not the function that we have found. At the moment, we found f prime, not f. So I'm going to use that information to figure out what is this constant. First, I'm going to try to simplify it. You can simplify 12 and 3. So this would be 4x cubed plus, you can simplify 6 and 2, 3x squared plus some constants. And we use the fact that f prime at 0 equals to -1. We use this fact that f prime at 0 equals -1. It means if you replace 0 with f prime, if I replace 0, I will get 4 times 0 cubed plus 3 times 0 squared plus c. This must add up to -1. This is 0 plus 0 equals c. So c must be -1. So what can I say about f prime? F prime x must be exactly 4x cubed plus 3x squared. And now since I found c, c must be. We're not done since we haven't found the original function f. So now what do we do to find f? We take another antiderivative. We go backward one more time. What would be the antiderivative of x cubed? It would be add 1 to the exponent, divide by the same exponent. You can skip over some step and say the antiderivative of 4x cubed is simply x to the power 4. I'm going to stick with this idea that you can simplify it later. 3 antiderivative of x squared is x to the power 3 divided by 3. What is the antiderivative of -1? Keep the negative. What's the antiderivative of 1? Simply x. And do not forget constant c. These two c's are not the same thing. So if you're using different constant, maybe you should mention this is c1, the other one is c2. Constant 1, constant 2. But since we already found that constant, the last part, and there is no constant anymore, I can use this c and represent it as a different constant. It may be -1, it may be a different number. So how do we find this new constant? We use the other information, the information regarding f, since we have the original function f. So let me simplify the function. It is x to the power 4 plus x cubed minus x plus c. And what do we know is f at 1 is given 0. So replace 1 into the function, 1 to the 4th plus 1 cubed minus 1 plus c must equal 0. It turns out in this case, actually, we kind of got lucky that c turns out to be -1. Maybe I should change this number so you notice that you do not always get the same number. Let me replace 2 here. The f of 2 is 0. That means if you replace 2 into the function, 2 to the power 4 plus 2/3 to the 3rd power plus -2 plus c equals to 0. So therefore, how do I find c? C would be calculate all these numbers, add them up. Maybe this was a mistake. 8 and 16 minus 2. So 8 and 16, that's 24 minus 2. C becomes -22. So what we found is f of x equals x to the 4th plus x cubed minus x minus 22. And here is a particular f function that satisfies all these properties. And that should be the only function that satisfies all those. If these two information, it's important to know that if these two are not given, then you do not get the unique function. You will have constant c showing up. These constants will show up. But with those information given, you should be able to find a particular function that a unique function that only satisfies those equations. Okay. I didn't write that many examples because the other ones, everything uses this property. So here I'll write this one as well. Given f of x, for example, f prime x is given as, let's say, 1 over 2 square root of x. And they ask you find out what is f. What you need to do is first write f prime x, because we do not have the antiderivative in terms of quotient anymore. You cannot use quotient rules since you want to go backward. And we don't have any formulas in the moment. So what you do is you try to rewrite this as 1 over 2 x to the power 1/2. I can rewrite that as 1 over 2 times 1 over x to the power 1/2. I'm going to break it down so you can see that these procedures are nothing different than moving this to the numerator and multiplying it by a constant. So now I can answer the question, what was the original function f? The 1/2 is still there. Add 1 to the exponent, x to the power negative 1/2 plus 1. Divide by negative 1/2 plus 1. Same exponent. So x to the power, you add 1 to the exponent, divide by the same exponent. If you simplify it, this is 1/2 x to the power 1/2 divided by 1/2. And it simplifies to just square root of x. These two will cancel out. And you get only simply square root of x. So what it means that if you take the derivative of square root of x, what do you expect? That. But is that the exact function? Not really. You should have a constant c, because any combination of any constant added to this function still satisfies the derivative to be 1 over 2 square root of x. Okay. You can use the trigonometric functions as well. Just one thing that I wanted to mention is very important. If the derivative is given x to the power negative 1, and they ask you find the original function, by adding this idea of adding 1 to the exponent, what do you get is negative 1 plus 1, negative 1 plus 1. This is x to the power 0 divided by 0. So here is the issue. Can you ever divide by 0? And the answer is no. So in this case, this is not possible. So therefore, if the exponent turns out to be negative 1, we cannot use this idea of adding 1 to the exponent and dividing by the same exponent for the antiderivative. Later on, we will discuss how to deal with this specific case. That's the only time that you don't need to use the power rule, and it's a logarithmic antiderivative. We'll discuss this when we get to that chapter, but I wanted to mention it. It's important that you cannot use that backward power rule for negative 1 exponent. Okay, I will stop at this point. And next time we will start on chapter 4.